All right, we'll go ahead and get started. Welcome everyone to Amaldi15's session 10-3 on stellar astrophysics. It's great to see everyone here. So we're going to start off today with a talk on deep Einstein at home, which should be a lot of, should be great. It's from Benjamin Steltner at the Max Planck Institute for Gravitational Physics. Take it away.
Thank you very much. So I don't even need to introduce myself anymore. So perfect, let's get started. Me set and okay, this is okay. I can see my mouse, so I'm clicking somewhere on the screen. So there are different types of gravitational waves. In the conference, we heard already about the short duration modeled one, so compact binary coalescence, and since the latest results of the PTAs, also a lot about the long duration unmodeled sources, but there are also long duration modeled sources, so-called continuous wave, which emit continuously. An important clarification, I will talk about continuous gravitational waves in the audio band, so advanced LIGO sources, not PTA or laser sources, where the possible simplest emission mechanism are non-axisymmetric fast-spinning neutron stars, which feature a mountain not aligned with the rotational axis of the neutron star, which continuously emit gravitational waves as long as the mountain is sustained and the neutron star keeps spinning. There are also other emission mechanisms, which I, however, will not go into detail about. Continuous waves have not yet been detected, since the gravitational wave amplitude is orders of magnitude smaller than the cataclysmic events of the compact binary coalescence events, but continuous waves are long-lasting, so it's possible to integrate lots of data to accumulate the necessary signal-to-noise ratio for a detection. Since the signal is buried in noise, we use a technique called matched filtering, where you convolve the signal waveform with the data. And in case the searched over signal waveform, so the template waveform, matches the signal in the data, some detection statistic gets excited. And if it matches less, it gets less excited until it doesn't match at all anymore. And then, depending on the detection statistic, we are looking at different statistical fluctuations. The signal model for continuous waves is fairly simplistic. If you are talking about neutron star mountains, it's twice the rotational frequency of the neutron star. And if the neutron star is spinning down, we also have a frequency evolution, so-called spin down. But we also need to take the sky location into account, since the detectors are on Earth, and Earth is moving around the sun and itself, so we have a yearly and a daily modulation, as we see in the right plot. Overall, the observation runs of advanced LIGO are on the order of half a year to 12 months, or the next one 18 months, and our signals there are really a lot of waveforms resolvable over a time span of a year. And with, let's say, 100 Hertz signal or so, there are really millions of cycles which we can track, and other way around, also have to track if we do a search over it. This makes continuous wave searches computationally quite costly, and how so depends on the amount of target information we have. If we have electromagnetic observations for pulsars, we know the sky location, the frequency evolution, and can in principle do a single template search, or within the small uncertainties around it. This is quite efficient, can do it on a laptop, and quite sensitive. If we only expect neutron stars, for example, in supernova remnants, or we don't see pulsation, so we don't get the frequency, we are looking at directed searches, which already can require a computer cluster. And if we don't have any target information, we are looking at all sky searches. So all over the sky and different frequency ranges, which are amongst the most computationally intensive gravitational wave searches. So one could ask, why go to the trouble of doing all-sky searches? Well, from electromagnetic observations, we know of more than 3,300 pulsars, but there are an estimated 10 to the 8 to 10 to the 9 in our galaxy, which, if they don't pulsate or if the beam doesn't sweep over us, are basically invisible, and with continuous waves are a population which then become visible by some other, basically spectrum. In fact, directed and all-sky searches are so computationally challenging that a coherent search is computationally infeasible, where with coherent I mean convolving or matching the signal against the full time span of data, since the necessary resolution grows with a steep power in the observation span, time span of the observation. So instead, we are doing semi-coherent searches where you divide the whole time span of data into a number of segments of now a coherence time, pico, do a coherent search in each segment, and then add the or get the detection statistic as the average over all these segments. This loses some sensitivity, but now the computational cost scales with the number of segments times the high power in these TICO, which is much less than the time span. A second technique to combat the high computational costs are so-called hierarchical searches, where we start with a less sensitive first stage. We call it stage 0, which, well, is less sensitive, but it's affordable, and less sensitive beats not doing the search at all. And then we identify interesting regions in the parameter space, sort of zoom in on them and search those with a more sensitive search. And we repeat this until basically the data is exhausted. Due to time constraints, I will not go into detail how this identifying works. Let's just say we are doing large-scale Monte Carlo simulations of injected fake signals, and we treat them exactly as the search results. And if we see that the fake signals behave in a certain way, we require the search results to also do so. Great. Let's come to the search. We searched for gravitational wave frequencies from 20 to 800 Hertz, this spin down range, and all over the sky, as the name suggests. We are searching for isolated sources, because if the neutron star is also in a binary system, we need to take the Doppler modulation of that system also into account, which becomes even more computationally challenging. We are using the O3a dataset. These are the first 6 months of the third observation run of advanced LIGO. And to cover this parameter space, in total, 7 times 10 to the 18 waveforms when necessary. If we would just use one GPU and calculate over all these waveforms, this would amount to 2,200 years of sequential computing. Since we don't really want to wait so long, we utilize Einstein Home and the Atlas supercluster, supercomputer cluster, to equal parts, where Einstein Home is a distributed volunteer computing project on the BOINC infrastructure, where volunteers, you and me, can spend their idle computational resources to crunch our numbers and advance our science case. And Atlas is the supercomputer down in the basement in our institute. And with these 2 great resources, it was possible to run this search within 1 year. Now, I'm skipping a bit here due to basically storage reasons, but also that we can't require the volunteers to upload gigabytes of data. And in the end, computational cost regions, we need to reduce the number of candidates, which we actually follow up in this hierarchical search scheme a bit. And we find these interesting regions in parameter space by some clustering method, which here we use this density clustering. And in the end, found the 3.5 million most promising regions in parameter space, which increased our search sensitivity the most, given the computational constraints we have. We then went into this hierarchical search scheme of ever more zooming in. And in the table left, you see after stage 7, we are fully coherent in O3a data, so no more segments. And at the end, we have 12 surviving candidates. We then went to stage 8, where we used O3b data, so the second half, which is slightly shorter, but of similar sensitivity, and did a search there. Since our continuous waves are persistent, so should be there all the time, this is great to have similar but a bit different data to V2 surviving candidates. In the end, we had 6 survivors after stage 8, which are 6 of the 7 hardware injections in our parameter search range, where hardware injections are fake signals put into the detector at the hardware level for pipeline validation purposes. We then went also into a final stage 9, where we used all of O3 data and kept also these 6 survivors. This, however, means that there was no continuous wave candidate left over. And based on our null results, we now set 90% confidence frequentist upper limits on the gravitational wave amplitude. We measure the upper limits because it can be quite difficult to model all the different steps in the pipeline. I didn't really go into the details here, but we are doing some noise removal. There are spectral artifacts in the detector which we remove, which basically also removes some part of a signal power. And since this is really hard to model, we measure the upper limits. We do this in every half hertz with a lot of signals, and basically then fit at the end the continuous wave amplitude for which we detect 90% of the target population. This we can see in this plot, where we see the frequency against the upper limits in gravitational wave amplitude. The red curve are the results of this search. In gray, we see 4 pipelines of the latest LVK all-sky results, and in blue is our sort of complementary small ellipticity, so small spin-down Falcon search pipeline. The stars denote the frequency and the injected gravitational wave amplitude of the hardware injections, and the I can't point on it now, but on the left side, the red star with the hardware injection ID 11 is the hardware injection we missed. And this we missed in the very first stage, since it was at a high mismatch point in our grid. The amplitude is a bit below our upper limits, so it's consistent. Since 90% upper limits means we do miss 10% of the signals at this amplitude. But nice is that we do find the hardware injections ID 0 and 2, which are way below our upper limit, which however is also consistent because below the 90% upper limit comes the 50%, etc. And all in all, I think the hardware injections are a great way to really assess a pipeline's efficiency. And this way we can be very confident that if there would have been a continuous wave at this amplitude, we would have detected it. With the upper limits on the gravitational wave amplitude, we can also set upper limits on the neutron star ellipticity. So how much does the neutron star deviate from the rotational symmetry? This can be expressed as this ellipticity for different. Would be great if I saw my mouse pointer. Well, for different distances d or frequencies f and a fiducial moment of inertia, we can arrive at the plot to the right, where we for different distances have the curves there at what frequency we can exclude certain ellipticities. So for example, for a neutron star spinning at 150 hertz, so 300 hertz gravitational wave frequencies, and a distance of 100 parsecs, we are looking at the blue curve, so we can exclude neutron star ellipticities at the level of 10 to the -7, which is something of millimeter mountain for a neutron star. Similar, we can set upper limits on the R mode amplitude These are unstable toroidal fluid oscillations in the neutron star, where again, for different frequencies and distances, we can set upper limits on the amplitude. So in summary, we did a search for continuous wave emission from isolated unknown neutron stars, did not find a continuous wave, but consistently recovered the hardware injections with a very high precision, using the complete data set of O3, the frequency within 1 nanohertz, spin down within 10 to the 15 hertz per second, and 0.3 arc seconds in sky, which I think really shows how precise continuous waves then can also track the spin phase of the neutron star. And all in all, set the most constraining Or-sky upper limits in the search parameter range. And with this, I thank you very much for your attention, and I take questions now.
All right, thank you very much, Benjamin. We could take questions both in the chat as well as via raising your hand. So if anyone has questions, go right ahead and start asking them. I'll go ahead and start us off, though, just because I'm a little new to this specific type of thing. Exactly how would a, say 1 millimeter bump occur on a neutron star's surface?
Yeah, that is the prime question. We really have a lot of models how these could form or be sustained. So one possibility is accretion, where, of course, this search then is not really fit to it, since if there's some accretion happening, then there must be something else, which probably isn't good for our waveform. But it could also be like star quakes in the neutron star, where the crust then breaks and is not immediately relaxing to the rotational symmetric shape. There are also models where the magnetic field can form these mountains, but I think there's not really a favored model so far. But there really are a lot of studies going into how these mountains can be formed and sustained.
Awesome. Well, thank you very much. If there are no other pressing questions, I'm going to go ahead and have us move on to the next speaker, just so we can try to eat up those times nice, and you guys can have a nice long coffee break once we get to the hour. So let's thank Benjamin again. That was a fantastic talk.
Thank you very much. If you just want to override my sharing, because I still can't see my mouse and I'm not sure I can hit the escape. Okay, never mind. Got it.
All right, thanks so much. All right, our next speaker is Alejandro. Do you want to go ahead and share your screen?
Perfect. So I just start. Hi everyone, my name is Alessandro Santini. I'm a master's student at the University of Milano Bicocca. And today I want to talk about some work I've carried out together with Professor Davide Gerosa in Milan and with Dr. Roberto Cotesta and Professor Emanuele Berti at Johns Hopkins University about the so-called Cook effective correlation. This is just the observational evidence in the AVK dataset that more unequal mass binaries tend to correlate with larger effective spins. This phenomenon was first highlighted by Thomas Callister and collaborator after the GWTC-2 catalog was released, and was later confirmed with the GWTC-3 data. And in order to estimate the amount and the degree of this correlation, the authors try to model the effective distribution using just a Gaussian whose mean and standard deviation were get free to evolve freely with the mass ratio. And they found that, quite interestingly, the two quantities are anti-correlated at 97.5 credibility. Now, probably the most interesting aspect of this correlation is trying to figure out where it comes from. And this is what we decided to do, since we tried to come up with a simple tree model which could still catch the overall trend of the observations that you can see in the 3 panels from the LVK companion paper, and could give us some glimpse about the origin of this phenomenon. And we decided to tackle this issue in the context of hierarchical mergers in dense astrophysical environments. We did this because repeated mergers allow us to, let's say, kill two birds with one stone, since high generation remnants we tend to show large spins, since, for example, 2G remnant will cluster around the spin magnitude of about 0.7. And if we pair one remnant of this kind with the first generation black hole, the resulting binary will likely be unequal mass because of the difference between the two compact objects. The problem about this method is that we cannot assemble these binaries in a naive spherically symmetric environment, which could be, for example, a star cluster or a globular cluster, because the spherical symmetry of the environment will translate in a q-effective distribution symmetric around 0, while in the plot I showed you before, we don't see any events in the left region of the parameter space. For this reason, we thought about switching the symmetry of the system to a disk, since this would allow us to kill the spherical symmetry that arises the problem. And actually, in a real astrophysical environment where both of these conditions can be quite easily fulfilled is represented by migration traps in agent disks. And of course, mergers in agent disks is a topic that has been widely discussed in the literature, also in the context of the correlation. And you can refer to the work of Kernan and collaborators about this. But these represent the ideal environment to assemble multiple generations of mergers. In fact, these are peculiar locations within the disk where the viscous torque changes sign. And this means that disk perturbers located at a radii bigger than the one of the trap will tend to migrate inward, while perturbers at smaller radii will tend to migrate outwards. This means that first generation black holes that are either captured by the disk or formed through disk fragmentation can migrate towards the trap and merge, leaving a heavy remnant spinning, which will hardly leave the binary, which will hardly leave the trap because the orbital velocities in this location can reach values up to 10 to the 4 kilometers per second. Now, all of this looks nice on paper and was our thought process, but now we have to actually check if the symmetry of the astrophysical environment could be the right knob to turn in order to explain and predict the correlation. So here I'm showing you how different binaries populate the Cook effective plane in presence of different symmetry configurations. Here, going from left to right, we can see just isolated field binaries where both the black holes of first generation, hierarchical mergers in a spherically symmetric environment, and you can notice the symmetry around 0 I was talking about. Why? The yellow RN plot represent hierarchical mergers in a disk configuration. And the difference that in the yellow plot, the binaries can either co or counter align to the orbital angular momentum of the disk, while in the last plot, they can only strictly co-align with the latter. And as you can see, in the yellow scatter plot, we still have a left wing that we do not want if we look at the actual observations, while in the last scatter, the symmetry configuration, of course, is efficient to suppress this left wing. And for this reason, we decided to build a model combining the first and the last panel of this plot. This means that we are building a population of black hole binaries, which are made by a bulk of isolated events, and with also contribution of hierarchical mergers that occur inside a disk environment. Since our main goal was to keep the model as simple as possible, just to focus on the role of the symmetry in this analysis, we came up with the model which depends only on 6 parameters. And among these, the first 4 simply describe the populations we use to model masses and spins for our black holes. And as you can notice, just using a bunch of power laws for the masses and the uniform distribution for the spin magnitude. And here, I just want to underline that we're using 2 different power laws for the binaries assembled in isolation and inside the dynamical channel, because previous works have demonstrated that the AGN disk itself may also harden the initial mass function of the black holes, and we want to take this into account. Now, the interesting 2 parameters of our model are the last ones, since this FHM represents the relative amount of binaries we are considering from the dynamical channel, and therefore, for example, values of FHM equal to, I don't know, 0.2 means that we are considering that 20% of our overall population assembled within a disk as hierarchical mergers of NG plus 1G black holes, while this lambda over here is the one that rules our hierarchical prescription. In fact, we are building this kind of binaries such that a single black hole accretes first generation remnants until it reaches a generation n max, which is sampled from a Poisson distribution with mean lambda. And the reason we're doing this is just to encapsulate all the property of the AGN disk that will actually have an impact of the number of subsequent mergers. And I'm talking, for example, about the viscosity of the disk, the accretion rate on the supermassive black hole in the center, the migration efficiency, because we are not looking at these parameters in detail because their treatment is out of the scope of our investigation, since, as I just said, we just want to catch the role of the symmetry in the resulting correlation. Now, all this is a very simple prescription, but we still manage to reproduce results which are in broad agreement with what the LIGO collaboration finds. Here, in fact, I'm showing again as black solid lines and the bluish field region, the median and 90% confidence interval that the collaboration finds for the parameters of the Gaussian I was mentioning at the very first slides. And we superimpose what we find if we build population with different lambdas in this case. And as you can see, for example, the lambda equal 1 case, which would be the central red plot, manages to reproduce quite well the evolution of the mean of the Gaussian with the mass ratio. And even if it struggles a bit more when it comes to the standard deviation, we are still well within the 90% confidence interval, which is a promising result, in our opinion, especially given the simplicity of the model we are using to build it. And now, since this looks at the very least promising, we are working to translate it into a paper that we hope to publish soon enough. But of course, all of this investigation has a number of caveats that it's important to underline. And first of all, I want to say that we have not performed any kind of model selection to select the best combination of parameters that reproduce the LIGO results, because we are not performing a natural Bayesian fit to find the best values of our parameters. All the numbers that put on this slide came from simplifying considerations of astrophysical nature. So, for example, we are using for the field binaries population the actual results of the LVK collaboration, and we are considering the group mass function for the black holes inside the disk, and also the other parameters were not fitted in order to minimize the distance between our points and the actual course of LVK. But other than this, we also have to mention that we are just considering 2 formation channels in building our population. We just have some isolated binaries and a contribution of dynamical assembled binaries inside the disk, while probably there are also other contribution to the overall population that we are neglecting here. And finally, I want to mention that among our strongly simplifying assumption, maybe the strongest, is the requirement that all the binaries strictly co-align with the disk. For this reason, we try to investigate also what happens when we introduce a possible misalignment angle between the binaries and the disk itself. Here, for example, in the plot on the right, I'm showing as the blue and oranges lines the 90% contours of the previous red scattering over here. And as you can see, if you allow the binaries to be misaligned up to 45 degrees, the distribution in the Cook effective plane slightly tilts towards smaller values of the spin. And as expected, because we don't have anymore all the binaries co-aligned. But overall, the difference is not huge, let's say. So our results are still quite consistent under this point of view. So now just let me sum up our work, saying that the observed correlation may still arise when considering mergers from dynamical formation channels, as long as these we model these in the right, let's say, configuration settings. And for this reason, we think that repeated mergers in disk environments can represent a promising formation channel for at least some of the LVK events. But of course, the current and future observing runs will tell us more about this. And we also have some plans for the future, as we would like to carry out an actual exploration of the parameter space to see if there is a patch of our 6 or 7 dimensional space, if we consider also the misalignment angle, which could actually produce in the best possible way the LVK results. And these are done, and thank you for your attention. I will take questions.
All right, thank you very much, Alejandro. Anyone have any questions? Simon, go right ahead.
Hey, thanks. That was really interesting. So I missed where your mass ratio distribution came from for your kind of isolated channel, but it looked like you had a tail extending to quite low mass ratios down to like 0.2 or something, which would give you, like this plot, for example, which gives you like red points, you know, kind of 0.20, where there's, you know, if you trust this gray region from Callister et al., you know, where there shouldn't be things. So I was just wondering where that mass ratio distribution came from, and if this implies that the mass ratio distribution should be truncated for that population.
Okay, you're referring to like the red scatter points, right?
Yeah, the red scatter points for your isolated population.
Okay, so our let's see, our isolated population in this slide would be the gray scatter points, while all the red points you see here are binaries we are assembling inside the disk. So also run for high generation black holes pairing with first generation ones because of the repeated merger mechanism we're implementing, and these give rise to the low mass ratio tail that you are mentioning. And let's say that we have points here where just in a region that is excluded by Callister, just because we are not implementing any other cut on the mass ratio. We are just letting the binaries to assemble dynamically. And so, yeah, these come from probably first generation black holes that are paired with very massive ones inside the AGN disk in our model. We don't have isolated binaries at such low mass ratio. We have a few at quite low mass ratio, but this is not very likely to happen with respect to the bulk that we have at Q close to 1. If these answer your question, or
okay, yeah, I think I slightly misunderstood your plot, but yeah, your answer made it clearer. Yeah, I think you just whenever you kind of need to not only predict, the correlation, but you also need to not have points in this parameter space where there are where there are no observations, right?
Yeah, sure.
All right. Any other questions? Once, twice. Oh, Christopher, go right ahead.
A similar type of question. I was wondering about this assumption of the Krupa power law for the black hole masses, and I was wondering why that was chosen. So I understand, the functional form, but I was wondering why we expect it to be Krupa-like.
Okay, so actually we tested, we followed the work by Young and collaborators about the spectral index of the mass function inside the disk. And as they do, they start with the Krupa mass function and look how the disk impact on the spectral index itself. And therefore, now I've shown results obtained with the Krupa mass function, as we were mentioning, but we have also tested different values of this exponent, and we have just seen that it doesn't have a huge impact on the on these plots, so on the evolution of the mean standard deviation of the effective distribution. It has just a marginal role in this, so we're not like considering an in-depth treatment of this value, since the impact of the parameter is not huge. But yeah, this is not the only value of gamma exponent here we have studied.
Okay, yeah, that makes sense. I'm just surprised that the difference basically between alpha and gamma. Okay, that makes okay. I guess it's flatter. You have more high mass things. That makes sense.
Yes.
All right. Well, let's thank our speaker one more time.
Thank you.
And we'll go ahead and go on to our next speaker.
And so my name is Wouter van Zeist, and today I'll be talking to you about my recent paper on gravitational wave spectral synthesis. This is a paper that has recently been accepted in Monras, and we can also find it in arXiv at this ID here at the bottom right. Now you may be asking, what is gravitational wave spectral synthesis? Well, we define this as simulating the cumulative gravitational wave spectrum of all the different binary sources that are within a stellar population added together. And notably, this includes all the different types of potential compact remnants, such as black holes, neutron stars, and white dwarfs, as well as the living stars. And this cumulative approach can give us insights on the population, even when it is not possible for our detectors to resolve individual sources within it. And this is analogous to the processes of electromagnetic spectral synthesis of populations, which has already seen some extensive research. One example of such being BPAS. Now, what is BPAS? BPAS, or Binary Population and Spectral Synthesis, is a code suite which simulates the evolution of a population of binary and single star systems from a wide range of initial conditions. Here we use this specific version of the models in our simulations. Now, what do we do in our simulations? Well, we simulate a stellar population formed in a single starburst with an initial population of 1 million solar masses. I place it at a distance of 1 kiloparsec, essentially as a solar population similar to a globular cluster. Now we get onto our results. So here we show a gravitational wave spectrum. Here on the x-axis of the plots is the frequency, and here on the y-axis is the strain power of the gravitational waves. Here it's quite relevant to note that the LISA can only detect gravitational waves above around 10 to the minus 4 hertz. So the LISA range is around the right half of these plots. Here on the left-hand side, we show population at around 100 million years after the starburst. Here on the right-hand side, it's 10 billion years after the starburst, so a bit later. And here, each of the different lines shows the spectrum of a different type of compact remnant binary. And we see here at the oldest ages, that's the highest strain here. This purple line belongs to the double white dwarf binaries, which is generally what we expect from other research on LISA sources. And the next highest is neutron star white dwarf binaries. But here it's quite interesting. At the younger age, here in our population, we see that the dominant gravitational wave source is actually neutron star white dwarf binaries by some margin, followed by black hole white dwarf binaries. Here in our population, we don't yet have any double white dwarf binaries occurring in the LISA band. Now here on this plot, we show same information, but here on each panel, we show a different binary type, and each line is a different age of the population. Here I'd like you to draw your attention here again to the bottom left, where you see that for the neutron star white dwarfs, they have quite a strong signal at around 100 million years, but it drops off quite quickly after that. And a similar trend for the black hole white dwarfs. Now here, instead of plotting the strain, we plot the number of systems that occur in each frequency bin. We generally see here similar trends to what we observe for the strain. At the early times, the neutron star white dwarf binaries are the most numerous types of binaries, whereas after 1 billion years, the double white dwarf binaries become the most numerous types of binaries. Also, the double white dwarfs are the most numerous types of binaries in the population overall, but many of these binaries are below 10 to the minus 4 hertz, so at frequencies too low for LISA to detect. Now here in this plot, we go back to plotting the strain, and we also bring in living binaries. Here, the red line is binaries of living stars. Green lines have 1 living star and 1 compact remnant. And blue lines have 2 compact remnants, as we showed before. And we see here that at the youngest ages of the population, 1 million years, the living stars have a high strain, but there are actually no compact remnants yet. Whereas at later ages, the strain of living stars decreases as more of these living stars evolve and become compact remnants. And correspondingly, the strain of compact remnants increases. Now, the highest strain actually overall that we see is actually for living stars, but this is at a frequency of 10 to the minus 6 hertz. So it falls below the LISA frequency range. And in generally, actually, all of the living binaries are frequencies too low for LISA to detect. Because if these binaries get too close to each other, they will actually interact via Roche overflow. Now here on this plot, we plot the total gravitational wave spectrum of all the living and compact binaries added together and show how this evolves over time at a variety of ages. Here the youngest ages here in blue at 1 million years, and the oldest age is here in red at around 10 to the 10.5 years. And each of these different panels shows this population for a different metallicity. Here, going from a metallicity about a 10th solar to a metallicity that is about twice the solar metallicity. And we see that the overall shape of the spectrum is similar for all the different metallicities. Now, there are some slight differences in, for example, this peak here at around 10 to the minus 4 Hertz, that peak here at around 10 to the 8 years, which is caused by neutron star and white dwarf and black hole white dwarf binaries, is a bit sharper and more prominent at higher metallicities than it is at lower metallicities, where it is spread out over more ages. Now here we overplot the LIGO sensitivity curve onto the total gravitational wave spectra. Here on the left-hand side, it is a plot with a high metallicity. Here on the right-hand side is a plot with low metallicity. This black line here is the LIGO sensitivity curve, and each of the colored lines is the population at a different age. We see for both of the metallicities that the gravitational wave spectrum of the population is generally above the LIGO noise curve from frequencies of above around 10 to the minus 3.8 Hertz. Again, the highest peak here is for living stars, but as we can see, this falls below the LIGO sensitivity curve. Though there are other proposed detectors, such as the Mu Aries proposal, which would have frequency bands that might be able to detect this peak. Now here we plot something a little bit different. We plot the total number of systems that would occur in the LIGO frequency range, where we just defined it as being above 10 to the minus 3.8 Hertz, where we would be able to detect it. And here on the y-axis is the number of systems, and here on the y-axis plots how this evolves over time. We'll again show high metallicity on the left, low metallicity on the right. See again, for both metallicities, neutron star white dwarfs are the most numerous binaries until around 1 billion years, after which double white dwarf binaries become the most numerous. Overall, we see there are slightly more systems in the lower metallicity than for the highest metallicity. And we also see there are some differences in the relative abundances of different types of compact binaries, depending on the metallicity. Particularly, we see here black hole white dwarf binaries are relatively more numerous at low metallicities than they are at high metallicities, shown by this green line here, which can be to do with the greater stellar winds that occur in systems with a higher metallicity. What we've also done is done this last process of calculating the number of binaries in LIGO frequency range for some populations resembling real open and globular clusters. We've done this by using some catalogs of these clusters and then using the mass and distance and age parameters from these catalogs. And for open clusters, we found that only a very small amount, like 8 out of 300 clusters, even have an expected number of binaries above 0.1. And only one in the whole sample had above 1 expected binary. And this occurs because open clusters are very young populations, so they have not had time to form very many compact remnants yet. And they're also quite low in mass compared to globular clusters. Now for globular clusters, we found 14 different clusters that would occur within 10 kiloparsecs of Earth, which would have at least 1 binary expected within the LIGO frequency range. And most of these being double white dwarf binaries due to the age of the globular clusters. And the most massive galactic globular cluster, Omega Centauri, we had an expected number of binaries of 12. Now we note there are some caveats with our results. For a population which would only have about a few binaries within the LIGO frequency range, the gravitational wave spectrum, as we see here, would not quite be a smooth line. It would actually have a bunch of individual peaks at the locations of each of the binaries. Another factor to note is that neutron star white dwarf and black hole white dwarf rates in BPAS the population that we use, are influenced by the implementation of mass transfer and common envelope evolution in the latest version, which is predicted to be a bit more stable than other populations might have predicted. And for details on this, there's a paper by Briel et al. In 2022. Another important caveat is that our binary population includes only isolated binaries and not binaries formed by dynamical evolution, which may occur in very dense stellar populations, such as globular clusters. And also, BPAS does not include certain physical effects, such as magnetic wind breaking, which would affect the double white dwarf binary rate. And finally, we note on some current and future work that we've been working on since completing this paper. One of those is creating synthetic clusters based on the BPAS models and evaluating how well LISA can actually resolve their gravitational wave sources using the software package legwork. The other thing we've been looking at is going beyond just isolated binaries and actually considering the effects of dynamical interactions as would occur in dense globular clusters upon the gravitational wave spectrum. And that concludes my presentation. Thank you for listening.
Awesome. Well, thank you very much for this really interesting talk. Are there any pressing questions? So I'll answer one as a dynamicist myself. So one thing I was thinking about through this whole talk was, about how crazy you can get in terms of the dynamic systems inside of globular clusters. So what's your more or less plan going forward to actually include some of these, dynamical interactions where you can have both tightening and breaking of these tight binaries?
Okay, well, it's a bit complicated to explain in a short time, but basically what we're intending to look at is sort of a semi-numerical relativity simulations based upon an earlier project done by a colleague called Lonely Planets, which was a project to look at the effects of dynamical interactions on planetary systems. And here we'll be using that to instead look at the effects of dynamical interactions on the binary evolution instead.
Yeah, that's fantastic. I'm very familiar with Maxwell Kai's work. I work with Simone quite a bit on this kind of stuff. So really awesome thing. Anyone else have any questions here? All right, looks like we're all good. I'll have to track you down and talk to you a bit about this a bit later in regards to Lonely Planets.
Sounds interesting.
Yeah. All right, next up, we have a little break. So we'll be able to eat up some of our time. We'll be reconvening here at about 10 past the hour. So thanks very much, everyone. We'll see you then. All right, so we are 10 past the hour, so we'll go ahead and ask that if you're in the other room getting some coffee or tea to come on in, back in, and we'll get started here. So let's see. Our next speaker goes talk on new lights on binary black hole populations from GWTC-3 and LIGO-Virgo.
Okay, thank you very much. So let's get started. I have already a couple of great talks on populations of black holes and how we can learn from them. So what I'm going to tell you today about how we can use the black holes that we have detected in the LIGO-VirgoKAGRA third gravitational wave catalog, our GWTC-3, to understand about the population of black holes and its connection with the underlying astrophysical properties which you can infer from electromagnetic observations, such as star formation rate, metallicity, and so on. So, our long story short, if I have to give you in one slide, what is our current status on our understanding of the cosmos is primarily driven by observations from electromagnetic probes, like cosmic microwave background, large scale structure, supernovae. And we have a fairly broad idea about how universe has evolved. So we had, at some point, the universe was completely dark. There's no stars, no galaxy. Then the first stars formed. Universe got reionized. Then the universe today we are completely ionized, but have a lot of galaxies. heavily star-forming galaxies, and now that's the epoch we are in, where it is a completely dark energy dominated universe. What I'm going to tell you about this picture of the universe, which you have observed from electromagnetic observations, can be tested and can be understood far better when we start using stellar graviers or black holes or any compact objects from low redshift to mid redshift range. And this will be possible by multiple upcoming or ongoing detectors on gravitational wave sector and across different frequency bands. I'll be primarily covering today on the results related to LIGO, but before getting into the results from the current ongoing detectors of LIGO, Virgo, and KAGRA, let us try to understand that why is this particular concept of let's understand astrophysics and cosmic history with binary black holes is even possible at all. So what I find is quite interesting about gravitational wave astronomy is that this particular probe is very informative in the domain of length, redshift, source, time scale. I call it LRS3. You can detect numerous sources across of different types, from binary neutron stars to supermassive black holes, which each of them varies from different time scales of the signal. Some of them are of the few tens of milliseconds, so some of them can be there for years. We can see these sources from redshift, very low redshift universe to very high redshift universe with the third generation detectors. And the physics which these sources can capture can be from a few kilometer scale to about kiloparsec scales to about gigaparsec scales. That means from the very nearby, the Schwarzschild radius of the black holes to the galactic scale physics or the star formation rate, which is imprinted on them, their population, to finally the cosmological scale where the gravitational wave is propagating and reaching. And this sector becomes quite interesting when you basically start seeing observations from not only in gravitational waves, but also from electromagnetic observations, which are excellent tracers of redshift, as a result of which you can possibly get a very nice understanding of the stellar metallicity and star formation rate in the universe and how it is evolving. So with that particular idea, now I would like to focus my today's talk on the topic of a multidimensional view on the black hole populations. At first, I'll talk about events. So in the left-hand side, you are seeing the quite well-known plot from the collaboration, where we have shown that O1, O2, O3a, and O3b, what is the typical population of sources we have detected across different masses, showing their both individual component masses and the total mass. But if I see a little bit different perspective of the same image, I can plot the primary masses of the sources as a function of the luminosity distance. Remember, this is completely from catalog. If we just take their mean values and plot it, of course, there's an error bar. I'm not plotting it over here. This is the plot made by one of my students, Aditya. You can see there exists neat correlations in the data between the gravitational wave sources, say the left-hand side topmost corner plot of masses with the luminosity distance. The interesting aspect to see here is that we do not see a lot of sources which are very heavy, very nearby. Though we should have seen if these sources are really there, because our detector is sensitive to seeing very heavy objects very nearby. So to get to understanding what we exactly are actually measure in the gravitational wave data and sort of to infer astrophysics from it, let me give you a little in summary about what we really measure so far from the gravitational wave data well. We can measure the sources of the gravitational waves, their masses, not truly their source mass, but the redshift nature of mass, which we measure very well. So our object at higher redshift will appear to be a little heavier than their true value because of this 1 + z factor coming from that cosmic expansion. And similarly, we measure also the merger rate of these sources as a function of distance. And if you take our cosmology as a function of redshift, so these are the two quantities which are quite well measured from the LIGO-VirgoKAGRA data. So the job in hand, what is our interest now, is using these binary black holes, can we trace the last few billion years of the universe. So that means if I have observed from electromagnetic sector the properties of galaxies, properties of star formation rate, stellar mass from different metal lines across redshift, if I want to connect that with the properties of the black holes that we see, what can connect them? In one side, I have to tell you about the galaxy in which the black holes are forming, the specific star formation rate in those galaxies, the stellar mass on those galaxies, the stellar metallicity, and other side, the black hole formation channels. Pretty much all of these are quite unknown to us because unless we do a data-driven search by combining both gravitational waves and electromagnetic observations. So what we now want to do is let us take a quick look at what have we learned so far from electromagnetic observations about the evolution of stellar properties in the universe. And how can we connect that to the black hole properties that we see in the LIGO-VirgoKAGRA catalog? So the left-hand side top plot, you are seeing the star formation rate from a plot by Emanuele Berti in 2014 as a function of redshift, which shows you that stars in the universe typically forms around redshift of 2, that's called the cosmic noon, and it falls down at the low redshift and also at the higher redshift. So depending upon different formation channels of black holes, there will be a delay time for formation of stars to mergers of black holes that will lead to a different merger distribution of black holes shown in the right-hand side of this plot. What you can see here, depending upon your different scenarios, unfortunately, we do not have a individual delay time distribution or how much each black hole gets delayed. We didn't know about it. But it's an effective parameter which at least can tell you on an average what is the delay time distribution. So the take home from the top panel is that a presence of delay time distribution, which depends on formation channels, will lead to a merger rate which can be motivated from the star formation rate in the universe. Second point is the evolution of stellar metallicity. This is again a plot from the Emanuele Berti 2014, where it is shown that as a function of redshift, if you plot the redshift evolution of stellar metallicity, metallicity goes down as you go to higher redshift. As metallicity goes down as you go to higher redshift, one of the key signature which it can play on the black holes is on the black hole masses. Stars which are metal poor end up giving you black holes which are heavier than those, at least in the first generation, than those black holes which are coming from metal heavy parent stars will end up giving you black holes which are little, lighter or smaller masses. And this correlation end up leading to a mixing of black holes at a particular redshift, because when you combine black holes coming from different redshifts because of their different delay time distribution, you may end up seeing black holes coming from very different metallicities, which is going to contribute to the LIGO-VirgoKAGRA catalog, which you are seeing. So now what we want to do, we want to apply this physics-driven understanding on the LVK observations to understand what can be inferred about the astrophysics from the binaries we have detected so far. Here I am showing you a plot of the combined posteriors of the catalog from the GWTC-3 catalog. In the left-hand side, for the heavier masses, we call it M1, the detector frame, as a function of the luminosity distance. In the x-axis lower panel, and assuming a cosmology shown in redshift on the top panel. For M1 in the left and the M2 in the right, M2 is by definition lower than the M1. What you can now see is that these sources, we want to fit these sources with our physics-driven model. So what we have developed is a Bayesian framework where we take gravitational-wave data, we take the corresponding prior on the delay time distribution, cosmological parameter, merger rate models. We call it the source parameter models. We combine that with gravitational-wave selection effects. And then finally, we combine this with the likelihood for both population and cosmology to get the posteriors on these parameters. So this work is done one of my student, Christos. What he has led this work. What he has shown is that the black hole population, which you have inferred from LIGO-VirgoKAGRA, when you combine them with the typical evolution of the star formation rate and metallicity, we get some very interesting insights about the black hole population already. So, of course, this plot is too messy to understand because it shows you a lot of parameters are strongly correlated. But I would like to take you through a couple of interesting results of this Bayesian analysis which we have performed. First, here is you are seeing a plot on the merger rate of binaries as a function of masses for different redshifts. So going from in green for redshift 0.8 to blue is 0.2. The main thing which you can start seeing is the black hole population which you have seen in the catalog end up telling you that there is a little chance that the black holes we are merging at a higher redshift may be coming from a little heavier mass than the ones that are coming at a lower redshift. Though it's at this stage too early to say conclude anything because of just we have around 90 sources, but the posterior distribution for merger rate as a function of masses indeed shows a little non-negligible redshift dependent of the black hole mass. What about the mass cutoff or the pair instability supernova mass scale? Theoretically, so several decades, I would say, there are studies have shown that black holes which are very heavy with their parent stars may not form a very heavy black hole because of the pair instability supernova, where a lot of material can be basically thrown away due to the wind. So you basically have a sharp cutoff in the mass distribution, which is shown in this left-hand side plots, that even if you have a very heavy core mass, black holes typically form around a redshift of 40-50, which is typically the pair instability mass scale. What you have found in the LIGO-VirgoKAGRA data that this little bump which you see in around redshift of 30-40, when you fit it with the metallicity evolution, it fits well with the metallicity evolution and the evolution of the redshift, and tends to agree that for different population models, the paired instability supernova mass range indeed exists between 35 to 55 solar mass from the current understanding on the star formation rate and metallicity. What next? Another interesting quantity which we have found is that what about the delay time distributions of the black holes? The delay time distribution of the black holes is currently not so promisingly constrained, but at least very large delay time distributions are ruled out. We see for different population models that they are mostly consistent with around 1.5 to 2 gigayears of typical delay time. Some of them are also peaks around around 500 megayears. If you want to play with population models, we have developed a code called GWSim. It is publicly available on this particular link. It's again by Christos. Here you can basically start using different mass, different spin parameters, different merger rate, different cosmology in a galaxy catalog to basically use and test how the population, different populations can be tested. So this is a synthetic catalog you can make. So please free to use this catalog. So with this, I will summarize this part of my talk, saying that what have we learned so far from the black hole population in the gravitational-wave third catalog is that there is a little agreement that the pair instability supernova mass scale is between 35 to 50 solar mass, which is in agreement with the theoretical one. The black hole naturally predicts a heavy mass distribution in the low redshift. There's a constraint on the delay time distribution. And what's very interesting is there's indeed a concurrent picture of metallicity star formation evolution with the universe with the black hole distribution we are seeing from the LVK. But this is not the full story. We have also stochastic gravitational background. And to give you a long story short, the stochastic gravitational background are those sources which are basically not detected by individual event, but are basically contributes to your energy density in the stochastic background. So if there are more sources contributing at high redshift, they will end up showing you a louder background of the in the stochastic signal. So one of the interesting work is that this high redshift population of black holes, which you cannot detect by individual event, can be seen in the stochastic background by not only the power spectrum, but also by something called as the non-stationarity of the stochastic gravitational wave background, which basically arises from the very fact that individual signal of gravitational wave are short in time and they have an intrinsic temporal dependence because of the chirping property. And this is present even in the stochastic background. So if you can estimate this signal from the gravitational wave data, what Mohit has shown in his work is that this leads to interesting correlation in the covariance matrix of the stochastic gravitational wave background, which you usually never consider in our analysis. And if you indeed consider that, you will start understanding on an average what is the population of black holes coalescing at higher redshift, above redshift 1, which basically contributes to your background from A+ design sensitivity. So these results are obtained from A+ design sensitivity for different black hole mass parameters. And as you can see, there is indeed a very interesting correlation in the covariance matrix shown in the left, top left and right panel for different mass distributions. The lower panel shows the Fisher results, which indeed shows that there are more information than just power spectrum, which is usually considered. With this, I will end my talk, telling that there is a very interesting data-driven exploration of gravitational waves using multi-band observations, where you can start inferring astrophysics, cosmology, and fundamental physics with several upcoming detectors, HLV, HLVK, which is some from 2023, currently ongoing, with LIGO India in future, and also LISA and Cosmic Explorer. So the take-home message from my talk is gravitational sources are the new probes for the high redshift universe. We can actually start learning about the stellar properties and the connection with the black holes through these observations. More sources will be detecting in future. It will be a neat probe. GWTC-3 hints towards a redshift evolving mass distribution of binary black holes. And finally, the non-stationary aspect of stochastic background can tell us about the high redshift universe. So with this, I will end my talk. Thank you so much.
Awesome, fantastic job. We have time for one really quick question, if there are any. Okay, so we're gonna have to go on to the next one just because we're right on that time limit. So we'll switch over to Simon's talk.
Cool. Yep. Thanks. Thanks a lot, and it's good to be here. Yeah, it's a shame that isn't in person, but hopefully next time. So I guess I'm going to be continuing on the theme of the last couple of talks and talking about what we can learn from the gravitational wave population of mostly binary black holes that have been observed so far, and particularly addressing this question, whether binary black holes that we've observed come from this chemically homogeneous evolution channel that I'll tell you a little bit about. So I think people have mentioned this already, but just by, I guess, way of motivation, as you probably all know, currently we have about 100 gravitational wave events in total that have been observed through these 3 observing runs, and we're currently in the early stages of this 4th observing run. So I have this little arrow here saying, we're somewhere near the beginning. But projections for this 4th observing run say that we should maybe double or triple the observed gravitational wave population that we will have in the next couple of years. And so this really kind of exciting and means that we can start to really use this population to answer some very interesting questions. And the one that I'm kind of most keenly interested in is understanding where these binary black holes are coming from. How do they form in the first place? And there's a whole bunch of different kind of theories for this. And Alessandro told us earlier about AGN disks. A few theories here on this slide. We have these 2 theories on the left that are kind of different variations of isolated evolution of massive binary stars, either from very wide binaries that are brought closer together through either common envelope or stable mass transfer. And in these very close binaries, we have this chemically homogeneous evolution channel that I'll describe in a little bit more detail on the next slide. And then alternatively, we have this kind of, dynamical formation, whether that be in star clusters or galactic nuclei, that, and each of these channels will make kind of different predictions for what the properties of binary black holes should be. So what their masses and spins are, for example. So we use this rapid binary population synthesis code that we've developed called COMPASS to model isolated binary evolution. So these two channels on the left. And I'm just going to kind of go into a little bit more detail about what this chemically homogeneous evolution channel is. So the idea here is that if you have two massive stars in a kind of very close binary, the two stars can become tidally locked to one another, and this can induce rapid rotation in the stars, and in turn that can lead to efficient mixing of the within the star, leading to them to become chemically homogeneous, so fully mixed. And this basically means that they can evolve directly from being hydrogen-rich main sequence stars to being on the helium main sequence. And so this means that you can essentially form binary black holes in situ without, ever undergoing mass transfer or common envelope evolution. And this channel has a strong preference for low metallicity environments. So in our previous study, we looked at the Chirp mass distribution of binary black holes that is predicted by COMPASS, and we allowed a bunch of parameters in our model to vary, which leads to all these gray squiggly lines in this plot. And what we found is that pretty much all of the variations that we considered predicted, on average, that binary black holes were too massive compared to the observations, which is this blue line from GWTC-3. And this also led to some other complications in terms of leading to biases in inferring some of these free parameters that we had varied. And the reason that we basically found out that this was happening is because we were having a very large fraction of the binary black holes in this model, something like 70–80% of the observable population, were forming through this chemically homogeneous evolution channel. So we wanted to try and understand why this was the case, and if there should really be so many chemically homogeneous binary black holes. One thing that we also noticed with the earlier study is that our models typically only predict binary black holes with Chirp masses up to about 40 solar masses. This is because of this pair instability supernovae that was also mentioned in the previous talk. But about 10% of the observed gravitational wave sources have Chirp masses higher than this, depending on what cuts you use and whatever. And so if we believe this prediction that, we can't form things more massive than about 40 solar masses, then this implies that there's a contribution of at least about 10% from another channel that can produce things that are that massive. So maybe dynamical formation. And, this could be seen as kind of a lower limit, because if you need at least 10% of things to produce these very massive things, then it's reasonable to assume that lower mass binary black holes can also be produced by whatever channel is producing these more massive ones. So in order to try and kind of bring our model into better agreement with the observations, we updated the model of chemically homogeneous evolution within COMPASS. We looked at updating a bunch of things. So we enhanced the lifetimes and luminosities of CHE stars to try and match more detailed models. We implemented rotationally enhanced mass loss. And we also used detailed MESA models to come up with a fitting formula that allows us to predict the spins of black holes formed through CHE. But all of these things are kind of turned out to be not that important. The kind of main thing that led to a big change in our results was this transitioning to Wolf-Rayet winds close to the end of the main sequence. So the idea here is that as I said earlier, you're in this CHE channel, you're essentially going from the hydrogen main sequence to the helium main sequence. And so at some point close to the end of the lifetime in this phase, the helium abundance on the surface of the star, which is this YS value here, is getting pretty high, and the star starts to look pretty much like a Wolf-Rayet star. And so we shouldn't be applying kind of O star, hydrogen-rich star mass loss rates to these types of stars, which we previously were, but we should transition to using a more appropriate mass loss rate for these, Wolf-Rayet stars, which are typically higher and lead to more mass loss. And so when we do that, this makes a big difference in our results. So model 1 here in blue is kind of the representative of where we started our previous study. Models 2, 3, and 4, you can kind of ignore. Those are where we sort of incrementally implemented these various kind of updates, and they make some difference, but overall not a lot, and in some cases even go in the wrong direction from what we were looking for. But the sort of big qualitative changes with Model 5, which implements this transition to the Wolf-Rayet mass loss rates, where we really dramatically reduce the fraction of binary black holes formed through chemically homogeneous evolution. And because those are preferentially more massive, we also shift the mass distribution to lower masses. As I mentioned earlier, we also implemented this prescription that allows us to track the spins of binary black holes formed through CHE. This is something that we also hadn't been able to do previously. And we typically find that all binary black holes have either completely negligible or low spins, typically less than sort of 0.2. And the gray lines here are sort of meant to be a representation of essentially the observations. So the agreement is not perfect in either of these plots, but we haven't tried to fine tune any of the parameters. So the fact that there's sort of in general agreement is somewhat promising, I think. And so what we did here is we did try to play with one free parameter that we had a problem with previously, which is the sort of the overall scale of these Wolf-Rayet winds. And so what we have is the detection rate of binary black holes on the x-axis, and as a function of this Wolf-Rayet wind mass loss rate parameter on the y-axis. And we find one model here in the overlap of these two shaded regions that simultaneously agrees with the observed binary black hole detection rate and constraints, independent constraints on the strength of Wolf-Rayet winds. And this model predicts that about 5% of binary black holes come from chemically homogeneous evolution. So putting all that together, we can have some constraints on the branching ratios of binary black holes. Something like 10%, or at least 10%, must come from dynamical channels based purely on mass. Our models say about 5% of things come from chemically homogeneous evolution, and the rest come from other isolated binary evolution channels like common envelope and stable mass transfer. So do binary black holes form via chemically homogeneous evolution? Maybe some do, but probably most don't. Thanks, and I'll take any questions.
Thanks, Simone, or Simon. Any questions here? Christopher, go right ahead.
Hi, Simon. On your plot of spins, that was the entire black hole population?
Yeah, so yeah, as I mentioned on the last slide, by the time you get to this model 5, most of the population here is things formed through common envelope and stable mass transfer. So that's really just the spin distributions of those channels. So there's a bit of a transition here from what I'm showing. we do also show the the subpopulation of CHE binaries in the paper, but I didn't show it here.
So that was anticipating my next question: is what's the typical spin for that you find for the chemically homogeneous evolution? Because I think that was traditionally predicted to be about 0.4.
Yeah, I mean they were lower than I was anticipating, and so it's actually turned out to be kind of hard. I was thinking that we'd have kind of a high spin subpopulation, but it sort of turned out that we didn't. I don't remember the exact kind of number off the top of my head, but I remember that, yeah, they were pretty low compared to where I was thinking they might be. So everything seems to give low black hole spins. This was based on the Boisson et al. Paper.
Okay. Any other questions for Simon? I'm going to butcher your name, so go right ahead.
That's okay. Just to thank you for the talk, Simon. Just to add to what Christopher was saying, the mass ratio and the spin distribution varies, as we have been observing from the gravitational wave measurement. The mass ratio and spins vary with the mass parameter. You can choose mass parameter to be a chip mass or total mass, but they vary. Spins become kind of higher for heavier masses, and mass ratio also vary with the masses. So I was just wondering, how does that commute with the chemical homogeneous evolution? Or have you given it a thought?
Yeah, I mean, so I guess in our kind of picture, some of that variation comes from the fact that this is a mixture. And so, yeah, maybe you have other channels that are contributing some of those. I don't think we looked specifically at any of these like correlations, like this q-chi effective correlation that, for example, Alessandro was looking at in his talk earlier. But yeah, I guess I wouldn't expect that we would naturally predict that. So I think you probably do need a contribution from an additional channel to sort of have two subpopulations that produce this correlation. But yeah, I haven't really looked at that too much.
Okay, thank you.
All right. Well, if that's the case, we'll go ahead and have a quick couple-minute break before we start up the next session, which will be at the 50-minute mark. All right, everyone, we're going to go ahead and start up with our next talk. So come on back into the room, that quick little break we had. Let's see here. I'll stop sharing my screen. So our next speaker here is going to be Ryuichi Takahashi. If you want to go ahead and share your screen.
Thank you for giving me a chance of talk. The title of my talk is Probing the Solar Interior with Lensed Gravitational Waves from Known Pulsars. So my talk is about gravitational wave lensing. And this talk is based on this paper. This is the abstract of my talk. Here we consider gravitational wave signal from a pulsar just behind the sun. So when the pulsar is passing behind the sun, the gravitational lensing by the sun causes amplitude and phase modulations on the gravitational wave signal. So from the modulations, one can probe the solar density profile. This is the introduction. And as you know, spinning neutron star is one of the promising gravitational wave sources. And in this section already, Benjamin Steltner gave a talk about neutron star search using LVK. So I skip this part, and in this talk we consider known pulsars as the gravitational wave sources. This is the previous works. And gravitational wave lensing by the sun can probe the solar interior, and the idea itself was proposed in the 1970s, so it has a long history. The idea itself is not new, and in 1980, Bonshogan did the study to take into account the diffraction effect, and they showed that the diffraction important for lower frequency, lower than 10 to 4 hertz, near the focal point. So diffraction effect decrease the lensing magnification, suppress the lensing magnification. And recently, Merchant 2020, they studied solar lensing of gravitational waves from a pulsar, and they roughly calculated the detectability of the lensed signal. But their interest was just detectability itself, so they did not consider the measurement of solar density profile. So in this talk, our purpose is, our motivation is extract the solar density profile from the lensed signal. And using the another method, helioseismology, solar structure is already precisely measured. The accuracy is less than a few %. So using gravitational wave lensing is another method, another method. And this is a lensing configuration. Here is a detector and the sun and the pulsar. And the coordinate is fixed to the sun, solar center. The coordinate origin is fixed to the solar center. And the lensed waveform can be obtained using a diffraction integral. And here we assume spherical density model of the sun. And in this figure, black solid line is the gravitational wave path from the pulsar and deflected at the sun and arrive at the detector. And here we consider a simple waveform. For unlensed waveform, we consider monochromatic wave with a frequency F. So simple waveform. And here H0 and Phi0 are constant amplitude and phase, respectively. And after lensing, the lensed waveform is given by this form, and gravitational lensing amplify the strain amplitude. So here AF means amplitude modulation, and phi F means phase modulation. So lensing modulates both amplitude and phase. And in the high frequency limit, in that limit, we ignore the diffraction effect. In that case, amplitude modulation is the same as convergence. Kappa is the same as dimensionless solar surface density, projected surface density. And phi F is 2 pi F times Shapiro time delay. And Shapiro time delay is proportional to projected solar gravitational potential. So we can probe solar surface density and gravitational potential from the lensed signal. And we searched for pulsars moving behind the sun in the Australian Telescope National Facility ATNF pulsar catalog. And there are 4 pulsars meeting the criterion. And these pulsars have frequency higher than 10 Hertz. And this table shows the information of the 4 pulsars, the name and gravitational wave frequency, and theta lat is ecliptic latitude divided by solar radius. And 2 pulsars, for the 2 pulsars, the strain amplitude, the current ground-based detectors already gave upper bound on the strain amplitude. And this cartoon shows the trajectories of these 4 pulsars behind the sun. And orange circle is the sun, and 4 pulsars are moving from right toward left. And x-axis is ecliptic longitude, and y-axis is ecliptic latitude. But the origin is fixed to the sun, to the solar center. And roughly crossing time is roughly half a day. And these panels show amplitude and phase modulation for these 4 pulsars. Left panel shows amplitude modulation as a function of the ecliptic longitude. The right panel shows the phase modulation as a function of ecliptic longitude. And you can see in the left panel, you can see the solar lensing. Solar lensing amplifies the gravitational wave strain about percent level, about several percent. And in the right panel, you can see the phase is modulated about 0.1 radians. So in general, phase modulation is larger than amplitude modulation. And as I mentioned, amplitude modulation traces solar surface density, while phase modulation traces the projected gravitational potential along the path. So along these passes. And higher frequency and smaller impact parameter pulsars are more suitable for probing the sun. Because, for example, among the sample, J7045 gives the predicts highest modulation, because this pulsar has the highest frequency. And so we calculate parameter estimation of the solar density profile. And at first, we consider the measurement of overall amplitude of the solar gravitational potential. So we replace the potential as like this, and A psi is a constant. A psi is the overall amplitude of the potential, and then calculate measurement error A psi using Fisher analysis. And here, capital T denotes the observational period, and pulsar is moving from right to left like this. The T equals 0 corresponds to here at the how can you say, at the longitudinal coordinate is at 0. And this is a result, a measurement error as a function of observational period. And in this, for these 4 pulsars, and in this plot, we normalize signal to noise ratio is 100 for 1 year observation. And from this figure, you can see SNR equals 100 for ear observation is needed to detect the solar lensing signature. And the error is smaller for a higher frequency pulsar. And next, we calculate the parameter estimation of the solar density profile. And the 2D solar density profile is divided to n annuli like this, from the center to the outermost part. The innermost part is first annulus, second annulus, and blah blah blah, nth annulus. And here we assume each annulus has the same mass. And then the annulus mass profile is replaced as sigma I is replaced with a sigma I times sigma I. And a sigma I is overall amplitude of the ith annulus mass. And here we while fixing the total solar mass. And then we calculate measurement errors of this the amplitude of mass profile, annulus mass profile. And the simplest case, this figure is the simplest case, n equals 2. So we divided the sum, the two annulus, inner annulus and outer annulus. This figure, y-axis is solar surface density as a function of angular radius. And dotted line, this one is boundary between the annulus, inner annulus and outer annulus. And these annulus masses can be determined within this error bars. And for example, red error is for J7045 like this. And here, SNR, we assume very high SNR, 5 times 10 to 4. So from this figure, we at least 10 to 4, SNR at least 10 to 4 for a 1 year observation is needed to measure solar density profile. And next, we consider 6 annuli case. And in this, the figure is the same as previous one. And first annulus, first, second, third, blah, 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 and the outermost annulus. And in this case, the SNR is set to 2 times 10 to 6. So it's really high SNR. And from this figure, SNR about 10 to 6 or 1 million is needed to measure the solar profile. And in general, a higher SNR is needed for a larger N. And this is a summary of my talk. And if you are interested in my talk, please check our paper. That's all. Thank you.
Thanks so much. Let's give our speaker a hand. Are there any questions here? So I'll go ahead and give one question really fast here. So if you were to go ahead and create an observing program to try and measure this exactly, what would be like your ideal case situation?
So as I said, among 4 pulsars, this one, J7045, is the most suitable to detect the lensing signatures. So this one, this has the highest frequency and the smallest impact parameters. So this is the best target for this purpose. Is it answer to your question?
Yeah, it does perfectly. So, and I guess the next question I would have following up on that is, so you need to look at 1745, like how often would you have to be observing the pulsar?
Yes, you know, these pulsars are how can I say it? In reality, in real situation, the sun is moving in the sky, annual motion. So this event can be observed every year, so annually observed.
Perfect. Awesome. All right. Any other questions? It's looking like possibly no, but it's a fantastic talk. It's a really awesome idea to go ahead and do something like this with pulsars to measure our sun's density profiles. Very, very interesting idea. All right, we'll go ahead and take like a couple-minute break. We're supposed to start. Oh no, I'm sorry. We are actually going to go on to our I guess 12-minute break now, but we'll be starting at 20 minutes past the hour for our next talk on first constraints on the binary black hole environments with LIGO-Virgo observations. All right, everyone, we'll go ahead and bring back the session to order. Hope everyone is doing just fine. You've got your coffee and your tea this morning or your evening, wherever you are in the world. We'll go ahead and get started with our next talk, which comes from Giada Caneva on first constellations of binary black hole environments with LIGO and Virgo observations. All right, take it away.
Hi, everyone. So thank you for the introduction. I'm Giada, and I am a second-year PhD student from IFAE, Barcelona. And today I'm going to talk about this work, which is the outcome of a collaboration of this list of people here. And the question that we want to address with this work, which hopefully is going to be out soon in the archive, so watch out for that, is basically, can we extract any kind of information about the astrophysical environment surrounding the LIGO-Virgo detected sources? So first of all, as we have previously heard from the other speakers, and I will not go too much into it, we have approximately 90 events from the past runs. Most of them are binary black holes. And generally, when the LIGO and VirgoKAGRA collaboration does searches or parameter estimation or population studies, these analyses are done based on the assumption that these sources live in vacuum, as we expect that the environment impact should be minimal, at least for the sources that are detected by the current interferometers. In reality, and we have also heard a lot about this on the previous talks, compact binaries might form and evolve in non-vacuum environments like active galactic nuclei, then star cluster, but also accretion disks. And it's interesting to study how the processes that take place in such environments affect the signals that we detect. And of course, in the literature, there is a lot of studies that are for future detectors, because of course they have the great sensitivity for these effects, but so far no one has looked with a proper analysis on how neglectable are these environmental effects for the data that we have. So the assumption that we base our work on, so the starting point is we take a compact binary that is formed and evolved in some kind of non-vacuum environment, like an accretion disk, which is characterized by a constant static density profile, and it's found in a quasi-circular state. So when we want to look for information from environments, where do we look at? So we look at the gravitational wave in spiral phase, because this by itself already encodes the information about the dynamics of the system. So if there is an environment around this binary, this will perturb the dynamics of the compact objects, and the information will propagate and will be encoded in the phase. So what we want is a binary that is sufficiently close to merger, such that the gravitational wave gravitational wave emission is leading the inspiraling, and the environment is only responsible for a subnominant, the phasing. And the environmental effects that can be taken into account are many. We have chosen to focus on the ones that also Cardoso and Maselli in this reference here focused on. So collisionist accretion, Bondi accretion, and dynamical friction. What we did, it's take a step towards the sources that we are interested in. So we have adjusted this expression in the case of stellar mass black holes. But basically what the takeaway point here is that we get expression that depends on the combination of the masses and density of the environment. And here on the right, you can see basically how the modified waveform taking into account environmental effects look like with respect to the one in vacuum. So one thing I want to highlight is that these environmental effects show up at low and negative post-Newtonian terms. So these effects basically come into play at very early stage of the spiral. And these also are quite easy to put in a parameterized form, which is quite convenient for us because in the LIGO-VirgoKAGRA collaboration, there is already an analysis, a framework that it's called, that produces a parameterized spiral test, which is basically taking a GR waveform, or for us, it's a vacuum waveform, and adding on top of this fractional or absolute deviation at the a specific post-Newtonian orders that we would like to do our investigation on. And this is exactly what we did based on the previous findings, but with taking a different step, in the sense that what I showed, those are very model-dependent expression for the phase shift induced by the environment. But what we want to do here is take an agnostic approach. So basically, we forget everything about the kind of environmental effects, and we just retrieve the information about where these environmental effects show up. So we add this absolute deviation at the minus 4.5 and minus 5.5 pm, which we have seen is where the environmental effects show up. We add this on top of our vacuum or GR waveform, and we perform a Bayesian inference analysis, which the outcome of this kind of analysis, the main outcomes are the magnitudes of, we can compute the magnitudes of these phase shifts by computing the posterior probability distributions, which here you can see for both PN orders and for each events in the first gravitational wave catalog, which are the events that we have focused our analysis on. And probably you notice that each event gives an order of magnitude that is different from the other. And if you look closely, you see that the smallest, tightest bounds come from the systems that either have low mass or are loud. And this is expected because, as I was saying before, these environmental effects show up at low frequency in the very early stage of the spiral. So the best probes for these effects are the systems that have low mass, so that we can access the many cycles in our detector band and extrapolate more information. And of course, if the signal is also loud, this also helps retrieving this kind of information. Another outcome of the Bayesian analysis is the computation of the Bayes factor. And very briefly, the Bayes factor is a powerful tool because it's basically a parameter that quantifies between two competing models, which one the data prefers. So we basically let the data decide between our environmental model and the vacuum model, which one fits it best. And we have computed this quantity for all events in the gravitational, for all events of the first catalog. And we have found that all the Bayes factor are negative. And since this is a computed as the ratio between the evidence of the hypothesis of environment and the one for vacuum. This means that the evidence for vacuum is greater. And so the data is basically telling us that it's preferring this model. Now we abandon the agnostic approach, and we go back to a more model-dependent framework. So we go back to those expression for the phase shift, and we invert them, and we get the density out of that, and we invert the relation of the posterior density distribution for the phase shift into density constraints for each appropriately for each PN to the corresponding environmental effects. But before looking into the data, we did some simulation taking three binaries as reference. So the first event, the lowest mass binary black hole, and the baryon neutron star. And we performed different sets of simulation for each environmental effects by varying the magnitudes of the phase shift, by fixing that at different magnitudes. And what these plots are telling us is basically that you have this threshold of the log base factor equal to 5, which is the detection threshold. So anything that is below that means that for a binary with the parameters compatible with those events and a density that is corresponding to one of the points below the threshold, we cannot detect the environment. So we cannot extrapolate the information on that. But everything that's above that threshold, we can extrapolate this information. And one check that we did was with this reference here from Fredo et al., where they didn't do the Bayesian analysis, but they did do a mismatch computation between, they had a numerical relativity environmental waveform for dynamical friction for binary compatible with the first event. And they computed the mismatch with both the first event data and a simulation in zero noise, which is the same. Also, we're doing simulation with design LIGO sensitivity. And what they find is that for a binary with compatible parameters of the first event, it should live in an environment with a density of the range of 10 to the 6th, 10 to the 7th, for it to be detectable. And this is exactly what we find. So I think it's very cool. But now let's go into the real data, and let's look at the constraints that come from the first catalog events. And as you can see, we get very large density constraints. So we perform the outline is that we perform the Bayesian analysis, we get the phase shift, we convert it into densities, and we get the very large values for the system that have large masses or are weak signals. And this is expected. There is the first event that's still very large system, but it had a quite large SNR too, so we get proper bounds. But of course, in the range of binary black holes, the two constraints that are the lowest are for 151226 and 170608, which are the lowest binary black hole in the first catalog. But looking at the whole events, of course, the binary neutral star is the one that's giving us the more information, since that is the lowest mass system. And for this, we get the tightest constraints. And just for reference here, I've plotted two density of reference, which is the one for the massive star collapse, which was discussed also by Fedro, but originally by Lo, which was an investigation on the first event being generated in a dump shell from a collapse of a massive star, and then also the thin accretion disk, but this is an upper bound. Okay, then very quickly, I just want to mention the future prospect. We didn't want to do large sets of injection for this, so we took this analytical odds ratio formula that it's very convenient to calculate future constraints on the densities. And we took these two binaries of reference, so the lowest mass binary black hole and the binary neutron star, and we fixed the log B to be 5, so for detection. And we, of course, ET, already with ET, we can go to very low densities, up to the 10 to the -3. But as in agreement with the literature that is out, we find that the future detectors are going to really probe the lowest densities. So just to answer very quickly, the initial question, can we detect any kind of environmental effects? Well, we don't find any evidence for that, at least for the event on the first catalog. But I think there are still nice open questions that we can address in the future. So thank you very much for your attention, and I will gladly take any questions.
Thanks so much. Do we have any questions here? Christopher, go right ahead.
Hi, so I understand you didn't find anything for GWTC-1, but naively I'd expect that, only a small fraction of events might be in a suitable environment any. So I was wondering if you have an idea of, how many systems you'd expect to need to look at in order before you find one.
So, I mean, I think so. This was like we looked at the events individually. So and for us, I think that we can probe densities they're lower and lower, or well, yeah. I mean, there is also the GW190521, which we have analyzed, and there were a lot of discussion over that, but also we didn't find any evidence for environment there. So for us, I think more than the fraction, I think it's very essential to have an accessible, good portion of the spiral. So I think the goodness of the analysis comes from having a clean signal that can give us a good window in those range of frequencies. Because of course, that event, for example, was a candidate, but since the spiral that was provided, it's not that much, we couldn't take out the information that we needed. So yeah, bottom line is that more than the fraction of events, I think the goodness of the analysis comes from accessing the range of frequencies that we really need to probe these.
All right, Wouter, do you want to go?
My question is, could you explain briefly what exactly it means, the difference between the collisionless accretion and the Bondi accretion, those effects that you talk about?
Yeah, so Bondi accretion is a type of accretion that is thought to be spherically symmetric, and usually it's related to higher density and high temperature accretion disks, while the collision and accretion, it's more suitable to describe accretion disks that have some kind of plasma, that it's less dense and quite colder than the previous one. But I'm not expert on this, so I hope that is naive answer.
Thank you.
Okay, and Juan has a quick question.
Yeah, just a comment. So you mentioned that you need a very long spiral in order to be able to access the environmental effects, because then you see the accumulated impact on the several cycles. But I was thinking that if your system is such that the ring down shows higher harmonics, then the amplitudes of these harmonics will be excited in a different way if the binary merge in an environment than if it merge in vacuum, because you will alter the dynamics of the collision and you will alter the initial geometry of the final object. So probably for high mass binaries, you can still see the effect if the ring down is strong enough and you see more than one quasi-normal mode.
Yeah, that's also true. Yeah, I mean, we try to think about how the ring down would look like in this case, and there are actually quite there is a bit of literature on this, like for example Barause et al, which was a long review on this. So yeah, that could also be another probe, but yeah, it depends if you also have a very strong ring down to look at. So
all right, thanks. Let's like our speaker one more time. We're going to go ahead and go on to our last talk of the session. Juan, would you like to go right ahead?
Okay, great. So hi everyone, I'm Juan Calderon Bustillo. I'm a sort of junior faculty here in Spain at the University of Santiago de Compostela. And the work I want to present deviates a bit from the main topic of this session, but it also tackles several assumptions or the validity of some assumptions that we do in standard LIGO-Virgo analysis, or the possibility of expanding those assumptions to more generic scenarios. So this work has not been done by me in isolation, of course. This is work that has been done with a large suite of very nice collaborators from Hong Kong, from Spain, from Portugal, etc., etc. So to start with, let me just recap the binary black holes that have been detected by LIGO and Virgo in the first 3 observation runs. We have them here ranked by the masses of the emerging objects and that of the final object. And actually two assumptions that underlie all of these parameter estimations that one does on these detections is, as Giada said, we assume that these things form in vacuum, or they happen in vacuum. And moreover, all of these analyses involve the assumption that these are quasi-circular binaries. So several studies have shown that some of these events may actually correspond to eccentric binaries. So how safe is the assumption that things are quasi-circular, or, as I will also discuss, these are even black holes? So let me remind you something that you all know, which is how a waveform from a black hole binary, from a circular black hole binary actually looks. You have this longing spiral that you see if the masses are sufficiently low, as Jack discussed. Then you have the merger stage, and then you have the final ring down. And the information that you actually have a quasi-circular binary, or that this merger happens in vacuum, or that these objects do not have tidal deformabilities, so that they are black holes, you can mostly read it. I mean, if you want to read it and extract it from the data, you need this very long spiral. But there are several events detected so far that do not show this long spiral. And the most paradigmatic example of these events is, of course, 190521, which is a signal that was detected in 2019 by LIGO and Virgo. And it corresponds to a very massive compact merger. So because of this, the in-spiral part, or the putative in-spiral part of the signal has a frequency that is too low to be observed by the detectors. And then we are left with what you see on the left, which is a very short signal for which you see the merger, the ring down, and if you're very optimistic, maybe a cycle of the supposed in-spiral. Now, if you analyze this event under the assumption of a quasi-circular merger, then you find very interesting properties. The first one that I do not explicitly show here is that the remnant is very massive, so it's an intermediate mass black hole above 100 solar masses, and also that the largest of the black holes in collision perfectly fills the peri-instability supernova gap that was discussed in Simon's talk. So this, in principle, presents a kind of a challenge, because in principle, peri-instability supernova gap prevents the formation of black holes in the mass range that I just showed, between sort of 50 and 130 solar masses, from stellar collapse. So you can automatically make the assumption, or try the assumption, that this may be a second generation black hole that was formed by a previous merger in what's called a hierarchical formation scenario. But this also has caveats of its own. For instance, if you want this to happen, then the escape velocity of the environment in which this black hole forms needs to be higher than that of the recoil that black hole inherits when it's born. And these recoils can get really, really large, of the order of thousands of kilometers per second. There are also proposals that this black hole could maybe be a primordial black hole, so you don't need to rely on any stellar collapse to form it. Now, because there is very short information about the pre-merger processing here, the 190521 allows for many interpretations. The main one of them, or the first one of them, was this one that I discussed, that it was formed through a circular merger scenario. And under that scenario, or under that assumption, you find that you need mild orbital precession in order to describe this waveform, or to reproduce this waveform with waveform models. But this effect is also degenerate with orbital eccentricity, as several people have shown. And therefore, there are studies that actually show you that this event is also consistent with an eccentric binary. There is also an alternative explanation that this binary could just have an intermediate mass ratio, so a mass ratio between 5 and 10, that would explain the morphology of the signal. But if you want to just throw options and options, you can even question the black hole nature of this event. So we get now in the realm of black hole mimickers. So black hole mimickers are essentially theoretical compact objects that lack a horizon and they lack a singularity in their centers. They can mimic most of the gravitational properties of black holes, including how they bend light and so on and so forth, or what kind of gravitational wave signal they emit when they merge. And there are several proposals for what these exotic objects may be. I'm going to focus on that of bosonic stars. So a bosonic star is, in essence, a self-gravitating Bose-Einstein condensate formed by ultralight boson fields. And as I said, is a compact object that has no event horizon. For data analysis purposes, which is what I can talk about, not really about the properties of boson stars themselves. A nice property that this has is that these things can have spins larger than 1 because they do not have a horizon, so they are not subject to the cosmic censorship conjecture. And if the boson has a spin 1, so if the boson that is forming the star has a spin 1, then these things can spin really, really fast. They are stable even if they spin. And you enter, or you are talking about what's known as a Proca star. So this is the type of boson star I'm going to be discussing. I was saying that this is very interesting for the purpose of data analysis, because the simulations for boson stars that we have right now, numerical simulations, are restricted to head-on collisions. So if you want to form a final black hole that has the high spin that the black holes that LIGO and Virgo are observing, you need very, very high spins, actually above 1 on whatever the objects that are colliding head-on, because you lack the contribution of the orbital angular momentum to the final spin. So Proca stars are going to have the same physical parameters as black holes and also Proca star mergers, so masses, spins, and so on and so forth. But they have, of course, parameters of their own, which are the oscillation frequency of the complex field that is forming these stars, and this determines the compactness of the star. I'll anticipate that the compactness of the stars I will be discussing are such that these stars are between 1.10 and twice as large as black holes, so they will be half as compact. And then the boson mass, the mass of the particle that is forming this star determines the maximum mass that this star can have before imploding into a black hole. And this is important because whatever massive Proca star that we form at the end of the merger, we want it to implode into a black hole so that we can see the ring down that LIGO and Virgo see for 1905-21. And the cosmological motivation for studying ultralight bosons is that many people consider them as viable dark matter candidates. So what do we have? We have been performing simulations of these head-on mergers of Proca stars. The models that we have are very simple, are almost toy models. We release the stars from quite a close distance and they release from rest. This means that they do not acquire a lot of speed before merging, and therefore the signal is going to be quite weak, as I will discuss later. Very importantly, we do not only include the quadrupole mode that is dominant for circular binaries, we also include the 2-0, which is co-dominant for this type of collisions, and also a couple of higher harmonics that do not really have an impact on the net emission. So this is just a representation of the catalog we have in terms of the oscillation frequencies of the two stars in collision. You can think of this as the spins. There is a 1-to-1 relation between the frequencies and the spins of the stars. So the frequency plays a bit the role of the tidal deformability for neutron stars in the sense that it ties the mass and the spin. And the diagonal here represents equal mass, equal spin stars, whereas the rest of the triangle represents unequal mass, unequal spins. The maximum mass ratios we will have here are 1.2. So in all cases, things are almost equal mass. So the reason why I showed the black hole merger waveform before is that now I want you to compare it with what happens for a boson star merger, which pretty much looks like a neutron star merger. So initially you have the two stars. When the two collide, you form this hypermassive Proca star, and then depending on the properties of this final star, you will have one destiny or another for the star. So if it's if it's not compact, if it's not very compact, it will not even collapse into a black hole. If it's compact enough, but not that much, it will survive for a time, emitting this type of pulses that you see in the green waveform. And if it's really compact, it will almost immediately collapse into a black hole, which is the case we are really interested when we analyze current observations of LIGO and Virgo. So this is just a representation of how the waveform varies as a function of the frequency of the stars for a case where the two stars have the same frequency. So this is the equal mass, equal spin case. And you see that not only the length of the waveform, but also the number of cycles you see varies quite significantly as you vary this parameter. So as Giada discussed a bit, what we want to do is model selection and parameter estimation on several LIGO-Virgo events that we have some hopes to be able to fit with our very short waveform. So this will be very massive events. So we compare GW data to black hole merger templates, and we compare it to our numerical relativity templates. And in both cases, we run Bayesian parameter estimation using this public code called Parallel Bilby, which we have adapted not only to treat numerical relativity waveforms, but also to directly employ not the signal strain, but the Neumann-Penrose scalar, which is what actually comes out of our simulations. And the reason we do this is that obtaining the strain from numerical simulations has some huge complications of its own that can lead to artifacts in the stranger structure. So in order to avoid those, we created this formalism that deals with the Neumann-Penrose scalar. The two analyses are completely equivalent, provided there are no systematics between your Neumann-Penrose and your strain. So that said, the figures of merit we look at are what Giada was mentioning in her previous talk, the Bayesian evidence for the Procastar versus black hole merger scenario, and of course, parameter estimates. Priors are very important. So here I'm listing the priors we use for the Procastar mergers and black hole mergers. The priors are common for the extrinsic parameters and the total mass, but because of the properties of black holes and Procastar mergers, we needed to apply different priors. So the most significant thing here is that for the Procastar mergers, we place a prior uniform in the triangle that I showed you that represents the two frequencies. Whereas for the black hole mergers, we tried two priors for the mass ratio, uniform mass ratio, and 1 over the mass ratio, because this if you do not this and the binary has a high mass ratio, you may not find the true values. And we also tried two limits for the mass ratio of 4 and 6. Importantly, when we look at the evidence for the black hole merger, out of the 4 analyses we do, we always retain the highest evidence for the black hole merger scenario in order to be conservative about anything we say about the Procastars. So on top of 1905-21, we analyzed 2 other events that are cataloged in the LIGO catalogs, although they have marginal significances. So these are 200-20 and 1904-26. And then this trigger that was found in a dedicated search for intermediate mass black holes by LIGO and Virgo. This has not been cataloged as a detection or a glitch, although there are reasons to think this may be a glitch. But importantly, the searches give this event quite a higher significance than for the other 2 events. So jumping into results, this just represents the best fitting templates for both the black hole and Procastar merger scenarios for 1905-21. And you can see that the 2 are quite similar, to the point that one would expect, just looking at these plots, that the 2 scenarios may not be really distinguishable, which is the case. And just for fun, I represent I show you the same 2 waveforms, but for this weird event that I just mentioned. You can see that the shape of this event is not really what one expects or typically expects from a black hole merger, unless there are some fancy properties involved, like the presence of strong higher harmonics in the ring down. As per parameter estimation, I will only highlight 3 things. First, because we use this compact objects that have spins above 1, then we obtain spins above 1. So that's something quite fancy. Then because our collisions, as I said, are intrinsically weak, we need a distance, or we find a distance that is about 10 times shorter than you obtain under the quasi-circular merger scenario. And this will have consequences that I mentioned later when you do model selection. Because of this, the source frame masses that we find are quite heavier. And importantly, 3 of the events show consistent boson masses, which I'll discuss later. So regarding model selection, this is what we find. So 2 of the events are mildly favored to be protostar mergers, with one of them actually fitting way better in terms of the likelihood you find with the protostar merger scenario. One of them is weakly rejected and the other is strongly rejected. However, as I mentioned before, the distance that you observe or that you obtain for these events has a strong impact in your model selection. And this is because any reasonable prior on the distance to the sources will favor intrinsically loud sources that you can place farther away, where you are expected to find more sources if you believe that the universe is isotropic and homogeneous. In order to understand the impact of this, and only with that goal, we remove this factor from the analysis, and then you find that 2 of the events happen to be strongly favored as protostar mergers. So there is no strong conclusion to be drawn from here, other than maybe, and only maybe, if we could perform circular simulations of these protostar mergers so that they become loud, and assuming that we would be able to form similar or to generate similar ring down signals, then our model selection may look like this. This is a posterior distribution for 2 of the events of the 2 frequencies. So a thing that you see here that is quite visible is this kind of beating pattern that you find across the omega-1, omega-2 space. And this is because of the following. These stars are formed by complex fields, so they will have a phase. And in particular, the 2 stars will have a relative phase when they merge. And the relative phase between the 2 stars that merge has a very strong impact on the emitted emission. Because our catalog is limited to a relative phase of 0 at the beginning of the simulation, then we only explore one possible relative phase at merger for each of these combinations of the frequencies. So the bands, the dark bands that you see basically correspond to similar relative phases between the 2 stars at merger. Now, going to the boson masses, these are the posterior distributions. First of all, they are informative, and second, 3 of them show quite consistent masses. So the last thing I want to discuss is, okay, none of the events gives any strong evidence for a protostar merger individually. What about combining them? So what you can do if you want to do this is to say, well, let's estimate what fraction of these 4 events may be protostars or may favor this scenario, given these individual base factors. This is quite a simple calculation. And if you do this, you obtain the curves for the fraction of protostars within the observed set, not within the underlying population that I show on the right. I will just pay attention to the dashed blue line, which is assuming a normal prior in the distance, and it's excluding this event that is not a confirmed detection. So you see it peaks at 0, but of course it goes or expands all the way to 1, but because one of the events weakly favors this hypothesis. Now, you can try to exploit the coincidence between the masses by saying, okay, let's, instead of the gray prior on the total mass, let's impose a prior that, for instance, corresponds to the posterior we observed for 1905-21. And then let's see how the base factors for these things as protostars would change. So you can compute this with what's called overlap integrals, and you can see that 2 of the events would increase their evidence by factors of 5.5 and 3. Of course, the inconsistent event would just decrease its evidence as a protostar. If you fold this into the previous calculation that I showed you, what you find now is that the blue dashed line does not peak at 0 anymore, but peaks at 0.5. And the only message that one should be extracting from here is that there is quite a lot of potential in trying to look for mass coincidence between these events in order to extract evidence or to obtain evidence for the presence of protostars in your observation set in the absence of one single event giving you strong evidence. I have an expansion of this study ready, but I believe I'm kind of running out of time. So I will just jump to the conclusions and take any questions if you happen to have any. thank you for your attention.
Thanks, Juan. Yeah, we're running really close to the hour. So we'll see if we have any questions from the audience. If not, I'll ask one question. I do not mean this in any kind of antagonistic way. I'm just curious. So I was wondering if you guys are, if some of these results are self-consistent with some of the results that have come out from the pulsar timing arrays recently on starting to rule out certain populations of boson stars.
So I do not know those results in detail. The results we have checked against pertain the possible masses of the ultralight bosons that may form dark matter. But importantly, these studies consider scalar bosons. So even with it done, even with that difference, the range of masses we find is consistent with current non-excluded ranges for scalar bosons. Nevertheless, we are discussing complex bosons. So those are the ones we would need to compare with. Regarding pulsar timing array, I need to look in the results.
Cool. Yeah, that was one of the first times I'd ever heard of boson stars when we recently did our new physics paper for nanograph. So, cool. But yeah, really cool stuff. Amazing talk. It's really great to learn all these things. All right, well, that I believe concludes our session. So thank you everyone for attending, and thanks all our speakers for giving fantastic talks. Our next session will start up in about, we do the quick math here, about 4 hours or so, and that'll be on compact objects. So thanks so much, and I'll see you all soon.